My name is Brandon Feldkamp, and my partner is Anna Hartford. This is our project presentation of the investigation of Android cell phone data logs. The data sets are from Kaggle.com as a part of the Sherlock experiment. About the Sherlock experiment. The Sherlock experiment is a large-scale smartphone data collection project. The experiment was conducted for a period of 2 years with 50 unique users. The users agreed to use a smartphone provided by the researchers for the period of their sampling. The goal of this experiment is to aid industry security professionals and educational researchers in finding better methods of detecting malware on smartphones. About the datasets. There are 15 datasets in total for the experiment. 7 of the datasets are push datasets. The data is pushed from the devices to the researcher's server based on the actions of the users. 8 of the datasets are pull datasets. The data is pulled from the devices and sent to the researcher's server based on predefined timing of logging. What's in the push datasets? The push datasets are composed of the following: call logs, SMS logs, screen status information, user presence indicators, broadcast intents, app packages, and Moriarty. What's in the pull datasets? The pull datasets are composed of the following: Table 0, T0, telephony, hardware, and system information, which is sampled every 24 hours. There's T1, geolocation, cell towers, and screen state information sampled every minute. There's T2 with energy, acceleration, gyro information sampled every 15 seconds. T3, audio and light information sampled every 10 seconds. T4 has battery, memory, and transfer bytes sampled every 5 seconds. 6, Wi-Fi. 7, Bluetooth. 8, application. More about the data. The full data set contains 600 billion data points, 10 billion unique records. We are using 2 weeks worth of data from one user. Sherlock refers to all of the data sets except Moriarty. Moriarty is malware that is downloaded by the user via Google Play Store. Moriarty leaves clues about his malicious activities, and we have to locate these clues by finding the correlations and anomalies within the Sherlock dataset. Our goals. We utilize Python techniques learned this semester to review, analyze, visualize, and correlate the data points between Sherlock datasets and between Sherlock datasets and Moriarty dataset. We find information that allows us to better understand triggers for malware that can be identified within a device's sensors. Our process. We downloaded the 15 datasets into CSV files. We read these files into Panda data frames. We use the Unix timestamp to match up data points between datasets. We use visualization techniques to see the data and help identify triggers and correlations. We look for identifiers, clues within the Sherlock datasets that will help us find Moriarty activity. Code sampling. So first we import the packets that will be used later. So we use NumPy, import time, we imported datetime, import pandas, and matplotlib, and matplotlib for inline so we can view it inside the notebook. We read in Moriarty and the T1 dataset from Sherlock. We create the data frame using panda read CSV and point it to the Moriarty seconds CSV. Here is some more code. The T4 data is very large, so this took some time. So we create the T4 data frame the same way you would read in the Moriarty table. We join the two files at the intersection of the user ID, otherwise leave the data out. This will allow us to see the intersection of the sensor data relative to the malicious actions performed by Moriarty. Then we print and look at the shape of the data frame. Here's a histogram of the total memory used. Here's another histogram of the session ID. And here are 3 graphs that show the overlap and the correlation of the Moriarty actions merged with the T4 dataset. Graph 1 is the total memory used. Graph 2 is the total CPU used. And graph 3 is the memory size free. So we can see that no correlation found with mobile bytes used. See the green line that remains at 0. This represents the Moriarty cross-reference. And there's the code used to plot the graphs. Free memory available for all polls of Table 4 as compared to Moriarty actions. And there's the code to the left of the graph, so you can see what we had to use to plot. There's the free memory during Moriarty, and they're all free memory. This is the Seaborn scatter plot of the total memory used during the Moriarty activity. You have the user ID to the total memory used. Then we have finding correlations with Table 4. Table 4 is a large data set, and it had over 869 matching rows with the Moriarty timestamps. In order to isolate them, we utilize built-in correlation and absolute value functions from pandas. We are able to print out the last 10 entries, which gives us the top 5 correlations. And then we have the code that we used listed. Heat map correlation of Moriarty actions to total free memory from T4. In order to map the T4 dataset, columns had to be removed. Here's the code that we used to remove the columns. We had to filter off some of the columns of T4 so that we could create the heat map. Here's the heat map correlation. You have session ID, total memory used, battery voltage, buffers, and active anon. So we had to merge Moriarty, T1, and T4. Looking for additional correlations between sensor polls and Moriarty, we combined the newly created subset data frame of Moriarty and T4 with the original T1 data frame. We see 1,443 matching timestamp rows and find additional correlations with geomean values from T1. Here's the code for the correlation. And then here is the heat map of the correlation. Looking at push data from app packages. App packages contain the SHA-1 hash value for each application of the user's phone. We used this to send a file to VirusTotal to determine if the phone contained known viruses. Here's our code. We check on a response file from VirusTotal. So here's the code for that. We checked for the responses. Our 2-week sample contained 82 unique SHA-1 hash keys. Our results didn't find any known malware with the exception of the Sherlock Moriarty application. 56 apps were screened as probably okay. 1 was not found. 24 were not application types scanned by the tool. Some of these included Palo Alto, Symantec, Invencia, CrowdStrike Falcon. Although this 2-week sampling didn't find anything, this is a very important tool to be able to use from within Python for malware detection. Here's the user presence dataset. Merging the user presence dataset with the timestamp on Moriarty's activities, we find that the user was present for some of the activities. This is a clue that helps us identify that the malware is capable of initiating actions even when the user is not present. So you have the user ID on the left and the session ID on the bottom. And this shows exactly what malware can do without the initiation of the user. Can user presence data help recognize phone theft and invalid access? The researchers of Sherlock Project believe that the information contained within the datasets can allow other researchers to create tools that will aid in theft. There are so many sensor readings that can be evaluated in combination with the user presence timestamps. There are time delays to be mindful, however, as the push data from the user presence is collected upon an user action, while the poll data is collected at intervals from 5 seconds T4 to 24 hours T0. Being mindful of this, we chose to look at T4 dataset since it has the highest rate of sensor data. Intersection of user presence with T4 in relation to total memory used. So this graph shows the dates from our sample and the total memory used from the user presence and T4. Future work. We have only begun to scratch the surface of what types of analysis could be done with the full datasets from this project. We were only able to analyze the 2-week sampling from a single user. Cross-referencing data points across all 50 users would allow researchers to find patterns with malware as it relates to user interaction and device sensor readings. In conclusion, we were able to take the Sherlock dataset and analyze and manipulate the data to learn about how malware may work on Android devices. Malware is capable of sending private information that can implicate you and your data in many ways. Thank you for watching, and if you have any questions, please post them on a discussion board and we will answer them as quickly as possible.